And welcome to another video. Today we're going to be talking about the ring extension structure theorem. So we assume that Rs are some commutative rings and that R is a subring of S. Assume that A is some element of R. Then the smallest subring of S containing both the ring R and A and the element A is equal to this set, which is the set of all polynomials on R which had the A substituted for X already. Substitute A for X, of course. Now, the proof. Well, we need to prove essentially three things, right? So, we need to prove three things. The first, that indeed it is, meaning this set, a subring of S. Also, for the ease of notation, we shall denote M, this set from up here. Now, given some polynomial fa and ga where a had been substituted for x, right? We have them from the set M. Then, and of course, fg from the ring, the polynomial ring X. Right. We have that f of a plus g of a is equal to the function f plus g of a, right? And this is also contained in M. It is contained in M because f plus g is contained in the polynomial ring Rx. And of course, the M is taken over the set of all polynomials, right? So this one is also here where A was substituted for X. So this is in M trivially. A similar argument could be made for the inverse element f of a, and the product like so. We know that the additive identity is in M, so for we know the additive identity is in M because the zero polynomial is in Rx. Now, the second claim we need to prove to get to our general claim is that that both R and the element A are contained in M. And by R here we mean the underlying set of the ring R. Alright, that's not so difficult to show. Well, by choosing, or by putting rather, f A equal to the constant term A, where for all A in the underlying set of R, we have the underlying set of R being a subset of M. So in other words, every single element from the underlying set of R is contained in M because it is generated by the set of polynomials, and if we put, and as such we can take the constant polynomials which are equal to every single element from the underlying set, and as such the elements of the underlying set are contained in M. Since the constant, or pardon me, the linear polynomial f is equal to x is contained in M, A is also contained in M. Because f of A must be contained in M, so f of A is in M implies A is in M. Right, so this proves the second subclaim, and now on to the third one and last one. M is the smallest subset of S satisfying these conditions. This one is the easiest. Consider any subring U containing R and the element A. By the closure property, because U must be closed under addition and multiplication. By that I mean these operations. They don't necessarily have to correspond to the usual addition and multiplication, of course. And thus, it must contain all, or it must rather contain for all I, AI, and their linear combinations. Thus, you must contain all expressions of the form, and now we have some u0 plus u1 times a plus u2 times a squared, etc. up to un times a to n for all n natural and un in contained in the underlying set of R. Thus, M is a subset of this U, and thus it must be the smallest. Hence, we have proven what we desired. So we have shown that it is a subring, it contains what it's supposed to, and it's the smallest possible, which is precisely the claim, and thus we conclude the proof.